In this video, we will be developing the stiffness matrix for a bar in 3D, as well as looking at the transformation matrix in 3D. So we are going to be looking at transformation matrix and stiffness matrix for a bar in 3D. So when I'm working in 3D, I have my global system X, Y, and Z. And we are going to be looking at an element, a bar element in space that extends between 2 points, 1 and 2. So I'm looking here at this bar element that extends between points 1 and 2 in space. The local axis of this bar would be X prime, and the bar extends between 1 and 2. Now this X prime axis makes an angle with the X axis, theta X, and it makes an angle with the Y axis, theta Y, and it makes an angle with the Z axis, theta Z. We can define the unit vectors oriented in the global system as I, J, and K. For the local system, we are going to be looking at the unit vectors along the X prime direction. I'm going to be having an I prime. And you can imagine we're also going to have a J prime and a K prime. Unit vectors along X prime, Y prime, and Z prime. Now, this bar would have 2 degrees of freedom with respect to the local axis. I'm going to have at U2, I will be looking at, at node 2, I'll be looking at a U2 prime, and at node 1, I'll be looking at U1 prime. In general, a vector may be described with respect to global or local coordinates. So if I want to describe a vector in the local coordinates, I may describe it as U prime, I prime, plus V prime, J prime, plus W K prime. Now this vector here is with respect to the local ordinates. That's why we have all the primes. I can describe it with respect to the global and still get the same vector. So I can say that this is equal to, with respect to the global, I can say UI plus VJ plus WK. If I take the dot product with I prime, then we get here U prime, I prime, dot I prime, that's 1. So I get a U prime. And then when you multiply J prime with I prime, I get a 0. And you multiply K prime with I prime, I get a 0. And then on the right side, I'm going to get U I dot I prime plus V J dot J prime plus W K dot K prime. Now we can solve for U prime as equal to U, and I dot I would be cosine theta x plus V J dot J prime would be cosine theta y, and K dot K prime would be cosine theta z. For simplicity, I can write that as U prime equal to U uppercase CX plus V uppercase CY plus W uppercase CZ, where CX is equal to I dot I prime, and this is equal to, if I know the ordinates of point 2 and point 1, and I'm looking for the vector here oriented along the x prime axis, or comparing the x prime axis to the xyz, this is equal to x2 minus x1 divided by L, which is equal to cosine theta x. Cy is equal to I prime dot j, which is equal to y2 minus y1 over L, or equal to cosine theta y, and CZ would be I prime dot k, which is equal to Z2 minus Z1 over L, which is equal to cosine theta z. For a bar element, we have 2 degrees of freedom with respect to the local axis. Namely, I have U1 prime and I have U2 prime. Now, U1 prime may be expressed in terms of U1 CX plus V1 CY plus W1 CZ. And U2 prime may be expressed as U2 CX plus V2 CY plus W, oops, I'm sorry, W2 CZ. I can put this in matrix form. So in matrix form, we have 2 degrees of freedom or nodal displacements. This u1 prime, u2 prime may be said to be equal to. And then I have here cx, cy, cz multiplied by u1 v1 w1, and then I'm gonna show my u2 v2 w2 here. So I'm gonna have 0, 0, and 0. And then here I have 0, 0, 0. And then I have cx, cy, and cz. We can simplify that to say like the D prime matrix, displacement with local axis, is equal to this transformation matrix T star multiplied by D, the displacements, nodal displacement with respect to the global coordinates. Please note that D prime here is a 2 by 1. T is a 2 by 6. And D is a 6 by 1. So T star is the transformation matrix. And by the same token, I can write or express the element nodal forces F prime with respect to the local axis as function of the nodal forces with respect to the global axis F using the same transformation function T. Now, if T is an orthogonal matrix, I can solve for D by multiplying by the inverse of T star. So if I want to solve for D, I would say D is equal to the inverse or the transpose of this transformation matrix multiplied by D prime. Likewise, I can say that F is equal to T transpose multiplied by F prime. Now we've already know the element stiffness equations with respect to the local axis. So we have defined F prime is equal to K prime times D prime. And as you recall, for a bar element, this K prime was a 2 by 2 and was equal to A E over L. And we had a 1, a minus 1, a minus 1, and a 1. So K prime is this 2 by 2 matrix. Now, our goal here is to establish or derive the element stiffness equations with respect to global axis. So we want to be able to write F as a function of D via the global stiffness, element stiffness matrix K. So now if I substitute for F here, I'm going to put T star substitute for F prime. So F prime, I'm going to write that as T star multiplied by F. Now this is equal to K prime multiplied by D. Now, if I substitute for D from this equation, I would say this is equal to K prime, and for D, I'm going to put the, this is D prime. So for D prime, we can put T transpose times D. Now, if I want to solve for F, I will get that F, then I multiply by T star transpose, both sides, because it's the inverse. So I get that F then is equal to T star transpose multiplied by K prime multiplied by T star multiplied by D. So our goal was to establish these element stiffness equation with respect to the global axis. And if you look at here, we have the force with respect to the global axis, displacement with respect to the global axis. And what I have here then is my element stiffness matrix with respect to global axis. So here, this is the element stiffness equation with respect to the global axis. Now we want to solve for this K. So we want to find the stiffness matrix for a bar element with respect to global axis. And let me emphasize here that this is in 3D. So we are trying to evaluate, or we're working to evaluate this K. So this K, and we know that in 3D, this is going to be a 6 by 6, is equal to this T star matrix multiplied by K prime multiplied by, this is T star transpose. This is a transpose here. Multiplied by T star. Now, please recall that this K prime is a 2 by 2. This the transpose of T star was a 2 by 6. The transpose of it would be a 6 by 2. So if you look at this, the outcome of this multiplication would be a 6 by 6. Please recall that T star was equal to Cx, Cy, Cz, 0, 0, and 0. And on the second row, I have 0, 0, and then 0, and Cx, Cy, and Cz. So this is my T star matrix. K prime, the 2 by 2, was AE over L multiplied by 1 minus 1 minus 1 and 1. When we complete this matrix operation, we're going to find that this K, the 6 by 6, is equal to AE over L multiplied by, on the first row, I'm going to get Cx star, first row, first column. And then I have a Cx Cy, and then I have a Cx multiplied by CZ. And then I have a minus CX squared. Then I have a minus CXCY. And then I have a minus CXCZ. Remember, a stiffness matrix is expected to be always a symmetric matrix along the diagonal. So I'm going to do the diagonal and the terms above, and then we're going to have symmetry. So on the second row, second column, I have a cy squared, and then here we have cycz minus cycx minus cy squared minus cycz. And then on the third row, third column, I have a CZ. Remember, the diagonal is always positive, and so we're going to get here a CX squared. Here I'm going to get a CY squared, and here a CZ squared. Minus CZCX minus CZCY and a minus CZ squared. And on the fourth row, fifth column, we're going to get CXCY and then a CXCZ. And here I'm going to get a CYCZ. So now if we look at this carefully, the diagonal is always positive. We have symmetry. And also, when we look at this and I partition it into 4 submatrices, you will notice that this is the same as this, and this one is the same as this, and these are the negative of the matrix here. So if I look at my partition or submatrices, I can define a lambda that is a 3 by 3 as equal to CX squared, CXCY, CXCZ, CYCX, CY squared, CYCZ, CZCX, CZCY, and CZ squared. So this is a 3 by 3 matrix. And I can say that my element stiffness matrix with respect to the global axis, K, this 6 by 6 matrix, may be described as equal to AE over L multiplied by a lambda, a minus lambda, a minus lambda, and a lambda. So this should be an easy way to remember it. So these are my submatrices. So here we have derived the global element stiffness matrix in 3D for a bar element, and we are going to be using that in the following video to work an example.